Welcome to the Certified Calibration Technician Preparation Training Program. This program is designed to help you pass the American Society for Quality exam to become a Certified Calibration Technician. My name is Gary Meyer, owner of J&G Technology, who brings you this integrated training package. My background experience spans across 50 years of measurements and metrology, beginning with employment at Northwest Airlines in 1958, maintaining aircraft and flight simulators using analog computers. Employment by Honeywell as a calibration technician and quality engineer introduced me to the importance of quality. This led to 7 years' experience working with specifications and customer service as a manufacturer's representative. My 11 years with Philips Test and Measuring Instruments enhanced my calibration and troubleshooting skills on complex microprocessor equipment. When Philips joined the John Fluke Company, they closed the Minneapolis Service Center where I was employed and placed me on the street. At this point, I started my own calibration and repair service, Meyer Electronics. During this time, I was invited to join the advisory board for the metrology program at Hutchinson Technical College, now known as Ridgewater College in Hutchinson, Minnesota. I was later hired by the college to teach classes in electronics, metrology, and computer systems technology, where I served for 13 years. After retiring from Ridgewater in 2001, I began my present career teaching and consulting in metrology. The ASQ body of knowledge is divided into 5 general sections, covering the following topics. 1. General metrology. 2. Measurement systems. 3. Calibration systems. 4. Uncertainty and applied mathematics. And section 5 is quality systems and standards. We will begin with section number 1 and sequence through the topics in that order. In the introduction to metrology, the following topics are covered. Base SI units, that is the System International type of units. We'll cover derived SI units, which are those that come from a formula or an equation. SI multipliers and conversions, which are needed to express numbers and also to convert between the English and metric systems. Fundamental constants that are sometimes used as standards. Some of the common measurements such as temperature and torque, humidity, and a number of others. We'll cover traceability of standards and the hierarchy of standards, and then measurement standards, and finally substitution of standards. There are 7 fundamental SI units. Each of them has a name and an associated symbol. It is believed that the first measurement used was length. Mass, the second unit, has the same name and symbol, the kilogram. We are all familiar with time measurements, as our lives are so often controlled by the clock on the wall or our cell phones. Without electric current, this training would not be possible. Thermodynamic temperature affects most measurements that we make. Measurements of the amount of substance is practiced within the chemical and pharmaceutical communities. Luminous intensity is important in our visual world of computer monitors, photography, and high-definition TV sets. Also note that the language of metrology often speaks in symbols. It is important to observe the proper upper or lower case for symbol letters as well as the context in which it is used. We will now examine the definitions for each of these 7 SI units. The metric unit for length is the meter, symbolized by the lowercase m. Length was first measured in terms of several body parts. A familiar measurement was the cubit, the distance from the person's elbow to the tip of the extended middle finger, equal to approximately 18 inches. The width of a man's hand was and still is often used to measure the height of horses. The current standard definition of the meter is the length of the path traveled by light in a vacuum during a very short time interval equal to a fraction of a second as shown on the screen. The base unit for mass is the kilogram. The symbol is also kg or kilogram. The unit is defined as the unit of mass equal to the mass of the international prototype of the kilogram. The actual artifact is a cylinder of platinum iridium material maintained by national measurement institutes. There are several measurements commonly performed in metrology in many of the labs. Review the list. The next few slides cover each of these measurements in greater detail. Perhaps one of the most common measurements made in laboratories is temperature. Dimensional, physical, and electrical calibration are all affected by changes in temperature. A highly used temperature measuring device is the glass thermometer. They typically come in three different types: a partial immersion, total immersion, and complete immersion model. The application to liquid measurement must be understood to arrive at the best uncertainties for each type. The partial immersion thermometer has an etched line just above the lower expansion chamber to indicate the depth of immersion. A total immersion type depends on the skill of the operator to immerse only the column of mercury or indicating fluid to arrive at a stabilized point. Complete immersion types are immersed to cover the entire glass. If the thermometer needs to be removed from the liquid, it must be read quickly to reduce heat loss during the reading. Our next common measurement is pressure. Pressure is defined as the force per unit area. Common units are Newton per square meter, also called a Pascal, or in the English system of units, pounds per square inch. Three types of pressure are listed: atmospheric, gauge, and absolute. A fourth one, sometimes called negative pressure, is the vacuum. Gauge pressure is referenced to atmospheric pressure, and absolute pressure is the sum total of atmospheric plus gauge pressure. Analog and digital meters are used for measuring a variety of parameters depending on the model. Most VOMs, that is volt-ohm meters, measure DC and AC volts, amperes, and ohms. Some models add features such as capacitance, frequency, diode checks, decibels, and temperature. Analog meters are a better choice for nulling or peaking operations, reverse diode resistance checks, and most semiconductor testing. Digital meters are easier to read, have better resolution, and usually offer a wider variety of measurements. A disadvantage of analog meters is the incorrect use of the many switch functions and multi-scale reading errors. The calibration technician is required to describe and use various measurement methods in the lab, including direct, indirect, ratio, transfer, differential, and substitution methods. Data from these measurements must also be handled and reported properly. You will be expected to define terms related to measurement characteristics such as variability, sensitivity, repeatability, reproducibility, stability, linearity, bias, specifications, sources of errors, measurement capability, and system capability. Section 2 covers these topics. We will review each topic as listed in this section, which includes measurement methods, measurement data, characteristics of measurements, IM and TE specifications, primary error sources, measurement systems and capabilities, measurement assurance programs. Several different methods of measurement are used in the calibration lab. Our study will take us through definitions for each method listed, along with a practical example. Some of the different measurement methods include direct, differential, transfer, ratio, indirect, and substitution. The direct method, as its name implies, means that the measuring instrument comes in direct contact with the measurand, or that item that is being measured. The value of the measurement is also read directly from the test instrument. This would also be true in dimensional measurements when using a steel rule placed against a part and the dimension is read directly from the rule. Differential measurements are implemented when the value of the unit under test and the standard are very close. Better resolution and sensitivity are then realized. In the picture, two voltage sources, one a standard and the other an unknown, are compared by connecting them in series with opposing potentials. The millivoltmeter then displays the difference between the two opposing potential voltages. A similar situation in pressure measurement applies a U-tube with opposing pressures applied to each end of the tube. Section 3 covers the topic of calibration systems. In this section, we will cover calibration procedures, standardization and adjustment methods, industry practices and regulations, environmental control of the calibration lab, calibration processes for IM and TE, validation processes, records and management, and official reports. Calibration procedures may have specific requirements if a lab is accredited to one of the documentary standards ISO/IEC 17025 or the Z-540-3. Document 17025 does not use the words calibration procedure, but states that you need a procedure or method to assure equipment meets proper specifications for intended use. The language of Z540 is more specific, not only expressing the use of a calibration procedure, but names the elements that it should contain. If you need to create a calibration procedure, help is available. Several branches of the military service have procedures for calibration. Another great source is the online organization called GIDEP, or Government Industry Data Exchange Program, at www.gidep.org. This is a free service to companies that have government contracts. The GIDEP database is a source of many obsolete calibration procedures from many manufacturers. If you need to create a procedure from scratch, NCSL, that is the National Conference of Standards Laboratories International, has a document to help you. The document is RP-3, Recommended Practices for Writing Calibration Procedures, and it can be purchased on their website at www.ncsli.org. The text also provides some useful guidelines. Some of the common calibration procedure components that you will find include the following items. The purpose of the calibration procedure. Just a simple sentence or two write-up on what the purpose of the procedure is. Secondly, the requirements for the procedure. You should reference any auxiliary documents, that is, such as ISO 17025 or Z540.3. You should list the equipment and supplies that are required to do the calibration. Also list right up front any special precautions, such as high voltage in electronic circuits, or high pressure in pressure calibrations. Tolerance, ranges, and uncertainties should be listed for the various calibration items. A very important part of that procedure is the step-by-step procedure, which directs the technician through the calibration procedure in a manner which will assure good calibration. Other calibration components would include how to take care of out-of-tolerance processing. If you find a value out of tolerance, how do you report that? This should have some procedure in the calibration procedure or reference to some standard operating procedure outside of the calibration procedure. Also, any required documentation, such as before and after data, should be included, any certs, shipping instructions, and so forth. Also, storage and handling should be included as a procedure component. Welcome to Part 4 of the Certified Calibration Technician preparation. This section covers measurement uncertainty and applied mathematics. You will be expected to understand measurement uncertainty terminology, also uncertainty budgets, a method of displaying all of the different contributors of error to measurement uncertainty, and also uncertainty determination and reporting, which includes methods of calculation, some of the statistics involved in measurement uncertainty, and also how to report measurement uncertainty. Let's expand this outline. Some of the terms included with measurement uncertainty are guard banding, TAR, which is test accuracy ratio, and TUR, test uncertainty ratio, bias, error, precision, resolution, repeatability, reproducibility, traceability, accuracy, and the percent of tolerance. Upper and lower spec limits are usually set by agreement between the manufacturer and the consumer. At the center of these spec limits, we would have a true value. To determine whether or not the product is within specification, we would need to make some measurements. The measured value, as shown here, is a little bit to the right of the true value, but it is still within the upper spec limit. With measurement uncertainty, we must also consider what is the uncertainty of our measured value. As shown here, we have a possibility or probability that our measured value lies within a certain range called the uncertainty. As long as this uncertainty range is within the upper spec or lower spec limit, we make a decision that the product meets specifications. Measurement uncertainty combines all the different errors or uncertainties into this single number. Here is an example of an uncertainty budget. It is a very simplified uncertainty budget in that the A's and B's have been listed separately. However, they are all combined in one calculation. To get an idea of what an uncertainty budget looks like, we have several columns. The column on the left is the source of the uncertainty. In this case, we are listing just three different ones: repeatability, standards, and resolution. For each one of those sources, we have an associated value in the next column. Repeatability, for instance, is 2.2. This could be in any units. However, the units for this particular example shows that all values are in terms of millivolts. Also, there is a column for the type, which shows repeatability as a type A, which means we have performed some statistical experiment and made some calculations to arrive at that 2.2 value. In a regular uncertainty budget, this would be listed in the footnotes, which are another very important factor that we shall cover later. The type of distribution is also listed then as a normal distribution, since we made some measurements and calculated some statistics. And the divisor in the next column is used to get us into a value that will be for one standard deviation. So the value 2.2 here is inferred as being calculated on the basis of one standard deviation, giving us a divisor of 1. The standard uncertainty then is calculated by taking our value, dividing it by the divisor column, or 2.2 divided by 1, gives us a standard uncertainty value of 2.2 for this line item. Some uncertainty budgets also include the variance column as shown in the next column to the right. We said that variance is just the square of the standard deviation. Therefore, 2.2 squared is equal to 4.84 as the variance. We proceed on the following rows to do the same calculations. Look at the one labeled standards. This would most likely be taken off of a calibration certificate for the standard that is being used. The value shown here is 3.56. Since we did not do our own statistics on this number, we must apply some type of distribution other than the normal. So we have a type B distribution in this case. Since we are taking off a value of the plus and minus spec limits, this would be a rectangular distribution, and we would have a divisor of 1.732, which is equivalent to the square root of 3, which is the divisor that we use to normalize a rectangular distribution into a normal value. The next column is standard uncertainty, and so we divide 3.56 by the divisor 1.732. Here we come up with a standard uncertainty of 2.05 millivolts, or squaring that gives us the variance of 4.203. The next one down is resolution, and if you recall, that is the application for a rectangular type of distribution. We have shown a value of 1 here, which means that the actual resolution of our meter or our measurement would be equal to plus or minus 1, or the total value is 2. This gives us an A value of 1, and so we have again the resolution as being a type B, rectangular distribution, and again it yields a divisor of the square root of 3. This gives us standard uncertainty of 0.577. Squaring that gives us 0.333 as the variance. As we mentioned previously, on most uncertainty budgets, we would take the A's and B's separately and then combine them in the final result. In this simplified version, we are taking all of the three variances, adding them together. We can add variances, but we cannot add standard uncertainties or standard deviations directly. And so we end up with a total variance of 9.376. And then we can calculate from that the combined uncertainty, which is the same as doing the RSS value of the standard uncertainty column. So taking the square root of the variance, 9.376, we end up with an RSS value, or a combined uncertainty for the three items of 3.06 millivolts. We also have something called expanded uncertainty. This is used in reporting uncertainties in uncertainty budgets, and you'll notice in the bottom of the column here we have K equals 2. and a capital U to indicate expanded. So since the RSS value indicates a standard deviation or one standard deviation, two standard deviations would just be twice that value, picking up twice the area under the curve. And so we would have 2 times the value of 3.06, one standard deviation, to arrive at an expanded uncertainty of 6.12. This would also be represented by a confidence factor of 95.4%. On the topic of rounding, you were probably taught in grade school that if the next number to the right of a number you are rounding is a 5, you round the number up. ASQ exams and good industrial practices employs a different method. The rule is to examine the number being rounded to see if it is odd or even. If the number is odd, the next number is 5, the number is rounded up. If the number is even, and the next number is 5, the number is left alone. This applies only when the next number to the right of the number being rounded is equal to exactly 5. Study the 2 examples and complete the rounding exercise in the workbook. Section 5 covers the topics of quality management systems, also quality control tools, quality audits, corrective action, and nonconformances. Here is an outline of the topics covered under quality systems and standards. A. Quality management systems, which is further broken down into 2 subtopics of system components and strategic and tactical processes. B. Quality control tools. C. Quality audits. D. Corrective action for nonconformance, with the subtopics of nonconforming material identification and impact assessment of nonconformance. Now let us delve into the first topic of the outline, namely quality management systems and system components. 6 tools available for measurement and improvement have been identified and are listed on the slide and in the text. Number 1, organizational leadership establishes a unity of purpose for an organization and maintains an environment suitable to meeting those goals. 2, organizations will be successful only if they have customers. Companies must focus on the customer and their wants instead of the product or service being provided. Number 3, performance management is a relatively new concept. It is defined as activities to ensure that goals are consistently being met in an effective and efficient manner. The concept is results-oriented versus completion of projects. The text lists some organizational performance areas. Number 4, measures and analysis is tied into performance management. A measurement method must be developed to capture and analyze management information. Number 5, employee training and development, another component of the quality management system, also known as QMS, is used to develop employee soft and hard skills. There are benefits to both the employee and the company when a good program is in place. Those benefits are listed in the text. Number 6, ISO states that continuous improvement should be a permanent objective of the organization. All personnel should become familiar with the tools and involved in the process. This concept should become a way of life. Next, we take a look at some models used for continuous improvement. 7 quality control tools are covered in this section. They include cause and effect diagrams, which are also called fishbone diagrams, or Ishikawa diagrams, after the gentleman that developed this system. Number 2 is check sheets, a simple way of keeping track of when things get done and how they get done. Number 3 is the scatter diagram. The scatter diagram shows the relationship between two variables. Flowcharts, number 4, are a good way of showing a process flow. Number 5 is the Pareto chart, named after Wilfred Pareto, who used this chart to show disparities in the economic system in Europe and later adapted to manufacturing and other processes to prioritize items to be worked upon. Histograms are covered in number 6, and number 7 are control charts. This completes the demo of the CCT self-study course. In addition to the full PowerPoint lecture on CD-ROM, you will receive the following items: a 261-page study guide text, an 83-page workbook of many worked-out examples and problems to solve, 5 typical practice exams, 1 for each section of the body of knowledge, a scientific statistical calculator, the TI-30XA or equivalent. Also, email support from your instructor during the course. For pricing and ordering information, visit our website at http://www.jg-technology.com or give me a call, Gary Meyer, at 952-935-1108. Thanks for watching. I'll be watching for your order.